Hello everyone, a very good evening to all. I welcome you all once again for this second interaction session on experimental physics course, which is being flowed this July 2025 session by NPTEL with the course code NOC 25 PH 51. Myself, Vivekananda Naik, I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So today we will be solving a few problems that will be based on the week 2 of the course experimental physics and some of the concepts that has been covered in the week's contents. So before solving this week's content problems, so we had a few problems that was uh, left out during the last interaction session on last Friday. So let's start solving those two problems, and then we will move towards discussing the week two contents. So now the question number 11 from the week 1 content, that is based, it is related to uh, screw gauge. So the question says a screw gauge has 100 divisions in circular scale. It has 100 divisions in circular scale and its least count is 0.01 millimeter. In measurement of the diameter of a wire, the following readings are obtained. Main scale reading is 2 millimeter. So the main scale reading we are getting is 2 millimeter. Then the circular scale reading is 8 divisions. Now the question is find the diameter of the wire. Options are option A 2.80 millimeter, option B 2.08 millimeter, option C 2.008 millimeter, and option D 28 millimeters. So these are the four options, and the question it is mentioned. So this question is based on screw gauge, and it shows the circular scale. It has 100 divisions and the least count is given 0.01 millimeter, and the data given for us is the main scale reading, it is 2 millimeters, and circular scale reading is 8 divisions. So with this information we need to find out the diameter of the wire. So what is the diameter of the wire? So I'll give you a few minutes to solve this problem, and then we will discuss what will be the correct answer. So the informations we had in the question. So the circular scale has 100 divisions and the least count is 0.01 mm. So before solving the question, let's discuss a few things about the screw gauge. So now here you can see in the figure, this is called as the screw gauge. So it has two scales. One is main scale and another is circular scale. So the main scale is like our linear scale only, linear meter scale, and it has least count of 1 millimeters. So for this case, it has least count of 1 millimeters. Then there is a circular scale which has in general 100 divisions. So for the question we are discussing, it was mentioned that it has 100 divisions. So here we can say, so you can see circular scale has 100 divisions. Now this is called as ratchet, and this is a thimble which is used to rotate, and when you rotate the thimble, this spindle it moves like this way. So if you rotate it in this way, this spindle it will move and it will touch this anvil. So when this touch uh, so when this spindle touches the anvil, then there will be zero reading. So now we depending upon the error that might be present while we are measuring the zero reading, we have three different cases. Like for slide calipers also we discussed in the last interaction session. It had a zero reading, and the zero error corresponding to the zero reading, there are errors. Sometimes there might be zero error present in that initial reading. So similarly here there are two scales. One is linear scale and rotating scale. So or circular scale we can say. So depending upon the position of the two zeros of the linear scale and circular scale, there are errors. So when the zero of linear scale coincides with the zero of circular scale, like this case, here it is called as no zero error. But when the zero of let me tell you one thing. Here what we are seeing, it has 50 divisions. So the example I am explaining you the concept of zero error. In this case, it has 50 readings, but our question it is 100 readings. So this reading is nothing but it determines basically the least count of the instrument. So as you see here, it has 100 divisions. So the least count is 0.01 mm, because the linear scale it has least count of 1 mm. But here in this case, as you can see, in the linear scale has 0.5 marking. So accordingly, it has 50 divisions. So here also the least count is for the screw gauge, it is 0.01 mm. The least count was 0.1 mm in vernier caliper, if you remember, but here it is again one order less, that is 0.01. So similarly, let's discuss the zero error case. So when the linear scale coincides with uh, the circular scale reading which is greater than 0, greater than 0 means 5, 10 or 15. So here we can say 0.05 mm is the positive zero error, because here 0.01 is the least count, and since it has 5, the 5 of the circular scale coincides with 0, so it has 0.05 mm positive zero error. Similarly, for negative zero error, it should be less than 50. That is from the opposite end. So this is 45. This is 0 or 50. So 0 or 50. So this is less than 50. That is 45. So here again it is minus 0.05 mm, which is called as negative zero error. So these are the three different types of zero error that might occur. So if you are discussing, so if you are measuring some substance using the screw gauge, so what is the way to measure? So the least count, first we need to know least count is pitch divided by total number of divisions. So pitch is basically the distance the circular scale travels after one complete rotation on linear scale. So the distance traveled by the circular scale on linear scale after one complete rotation is called as pitch. So this is distance moved by a screw and number of rotations given. So here you see uh, after one rotation it will move 0.5 mm marking. If it moves 0.5 mm marking, its least count is 0.01 mm. But if it moves 1 mm marking, then its least count will be 0.02 mm, like that. So now how to measure the value? So first it will be linear scale reading, then circular scale reading, and if there is any zero error, it will be subtracted from that value. So let's discuss our current problem. So it was main scale reading was 2.0 mm. So main scale reading was 2.0 mm, and if you talk about the zero error, since there was no zero error mentioned in the question, so we can assume that there was no zero error. Zero means no zero error. Again, what is the circular scale division? So in circular scale it had 8 divisions. So circular scale divisions, circular scale divisions, it's 8. We know the least count. The least count is 0.01 mm. So what will be the measured value? The measured value will be main scale reading plus circular scale reading, that is main scale reading plus circular scale divisions into the least count. So it is 2.0 plus 8 into 0.01 mm. So what will be the diameter? It will be 2.0 plus 0.08 mm, which is equals to 2.08 mm. So this is the answer. So correct option is option B, 2.08 mm. I hope this is clear to everyone. Now we will move to the next one. Question number 12, the last question. Sorry, I think let me check again. Okay, so actually the slide is misplaced. So we need to this slide, we need to move here. So question number 12 says, if you write the number 323 to two significant figures, then it will be, options are option A 300, option B 320, 320 basically, and option C 330, option D 325. So the question says, if you are writing the number 323 to two significant figures, then it will be. So we know for here, if you see 323, it has how many significant figures? It has three significant figures. Because all are non-zero, all are non-zero digits, and there are no power or there are no decimal signs in this number 323. Now if you need to convert it to two significant figures, then we need to replace one of the one of the digits. So here generally we replace the 1th digit, which is 3 here. So in 3 to 3, these 3 should be replaced to 0. then it will be having two significant figures, because we know all the trailing zeros are not significant. So if we are replacing this 3 with 0, then it will be having two significant figures. But the question is, when we are replacing this 3 to 0, then will there be then we need to change the previous digits also, because since here uh, we are replacing from 3 to 0, this digit, it will again be replaced by some other digit. It might be replaced, but in certain cases it doesn't get replaced. For example, here also you see 3 is present, so 3 is less than 5. So when less than 5 is present, then we don't need to change any digit here. So 323, if we reduce, so 323, if we reduced to two significant figures, it will be 320, because 3 is less than 5. So I hope this is clear to everyone. Now we will discuss about the course concept that are covered in week 2. So if we discuss the concept that was covered in week 2 lecture, so it was mainly uh, discussing voltmeter, ammeter, and multimeter. How? So in the last week we discussed about the moving coil galvanometer, and generally moving coil galvanometer is used to measure small currents. Now, depending upon the circuit, we can convert the moving coil galvanometer into voltmeter and ammeter. So as I have already discussed, in order to convert galvanometer into voltmeter, we need to connect a high resistance in series, and for ammeter we need to convert a low resistance in parallel, which is called as shunt resistance. Now similarly, multimeter is another type of measuring device which is used to measure all the physical electrical parameters like resistance, capacitance, voltage, current, and sometimes it can also be used to measure the VI, measure the photodiode, diodes, LEDs, and all. And the other concept that was covered included resistors, capacitors, inductors, and wire connectors family. Then lectures was also covering cathode ray oscilloscope, and under basic analysis there was data collection, graph plotting, calibration, and error. So let's solve a few problems that are based on the week's contents. Now question number one. Question number one says, find the wrong statement. The question says, the statements are, resistivity of a conductor is independent of, options are option A, length, option B, temperature of the conductor, option C, shape of the conductor, and option D, area of cross section of the conductor. So let me rewrite the question. Actually it's a bit confusing. Find the wrong statement. um, the question is, resistivity of a conductor is independent of, so the resistivity of a, so we need to find out resistivity of a conductor. So there are different factors, whether they are affecting the resistivity or not. So we need to find out independent of means we need to find out the parameter that the resistivity is a dependent of that parameter. So options are option A length, option B temperature of the conductor, option C shape of the conductor, and option D area of cross section of the conductor. So I'll give you a few minutes to think about this question, and then we will discuss what will be the correct option. So now if we discuss this question, we know the resistance of a conductor is given by the expression R is equals to rho L by A, where this is the resistance, this rho is resistivity, this is length of the conductor, this is area of cross section. But here the question says the resistivity. So now if we discuss about the factors that affect resistivity, so one of the major factor that affects resistivity is the type of the material. For example, we know if you are talking about the electrical conductivity, the charge carriers or the carriers of electric electric current inside a material are electrons or free electrons. They generally govern the electrical properties of the material. So depending upon the material type, there will be different resistivity of the materials. So the factors that decides or the factors that are dependent upon the resistivity, resistivity is depending upon the material type, the nature of the material. Also, impurity is also a factor that determines the resistivity of a material. But if you see the length and the shape of the conductor, they are not affecting the resistivity. They affect the resistance because resistivity are independent of length. So resistivity is not resistivity does not depend upon length. It does not depend upon the shape of the conductor, and it does not depend upon the cross section of the conductor. So basically, shape of the conductor, it includes area of cross section and length. Basically, the shape also explains the length and the area of cross section. Now the only option that remains is temperature of the conductor. So now if you um, generally the resistivity is given as a function of T, that is temperature, as rho T that is at a particular temperature, rho 0. Rho 0 means the resistivity at absolute 0, 1 plus alpha T or alpha T minus T0. So here alpha 0 is, so let me write it again. So T is rho T is equals to rho 0, 1 plus alpha T minus T0, where rho 0 is rho at T0 and alpha is temperature coefficient of resistance. Temperature coefficient of resistance. Basically, it determines whether the resistivity increases or decreases with temperature. So when with increase in, suppose with increase in T, resistivity decreases, then we will say that alpha is negative, that is it has negative temperature coefficient of resistance. When with increase in T resistivity increases, then alpha is positive. So you can clearly say when alpha is greater than 0, alpha T will be greater than alpha 0, that is resistivity increases. So when resistivity increases with temperature, then it will be having positive coefficient of resistance. When resistivity decreases with temperature, it is called called as negative coefficient of resistance. For example, if you talk about conductors, for conductor resistivity increases with temperature. So it has positive coefficient of resistance, positive temperature coefficient of resistance. But for semiconductors, since they have a very limited number of free electrons, when we increase the temperature, then more free electrons gets we get more available of free electrons that conduct electricity, due to which the resistance decreases. So for semiconductors, alpha is negative. For example, if you talk about alpha, it is positive for conductors and negative for semiconductors. So temperature affects the resistivity, because depending upon the temperature, the motion or the movement of electrons or free electrons inside a material is determined. So resistivity of a conductor is dependent upon the temperature. So the correct option is option B, and this option B is the wrong statement. So the resistivity of a conductor is dependent of, so we can say the resistivity of a conductor is dependent on the temperature. So now let's move to question number 2. Question number 2 says a galvanometer having resistance 3 ohm is converted into an ammeter by connecting a 3 ohm shunt resistance across it. In order to double the range of the ammeter, the additional shunt resistance to be connected across it is, options are option A 3 ohm, option B 2.5 ohm, option C 2 ohm, and option D 1.5 ohm. So these are the four options given, and the question says a galvanometer having resistance 3 ohm is converted into an ammeter by connecting a 3 ohm shunt. So the resistance of the galvanometer is 3 ohm, and it is converted to into an ammeter by connecting again a 3 ohm shunt, that is the 3 ohm resistance or the 3 ohm resistor in parallel to the galvanometer. Now we want to increase, or we want to double the range of this ammeter. So the total current that was flowing through this ammeter, we want to double its range. So the current now will be flowing. We need the current to flow twice that of the initial case. Then what will be the change? We need to connect an additional shunt to the circuit. So the additional shunt, it need to be connected, and we need to find out the value of that shunt. So these are the two options. So these are the four options: 3 ohm, 2.5 ohm, 2 ohm, and 1.5 ohm. So not exactly this type of question, but similar types of question we have discussed in the last interaction session also. So I hope you will be able to answer it. I will give you a few minutes to think about this question and try to solve it, and then we will discuss what will be the correct option. So let's start solving this question. Now let's draw the ammeter circuit. So we know in order to convert a galvanometer into an ammeter, we need to connect a low resistance in parallel, which is called as shunt resistance. So this is the galvanometer, and this is the total current I that we need to flow to the circuit. So this is the initial case. So here, what is the condition? So when the galvanometer is connected, so the current Ig that will flow through the galvanometer, so the full scale reading is Ig for the galvanometer. Then the remaining current, that is I minus Ig, it will flow to the shunt resistance. So here in this case, we get Ig into G is equals to I minus Ig into S. So here G is 3 ohm, because here it's mentioned the galvanometer having resistance 3 ohm. So G is 3 ohm. This shunt is also 3 ohm. So G is 3 ohm, S is 3 ohm. So Ig into 3 is equals to I minus Ig into 3. So 3Ig is equals to 3I minus 3Ig. So 6Ig is equals to 3I, or Ig equals to I by 2. So in the next case, we need this value of Ig, because this will remain constant. So this is the current, or the full scale current through the galvanometer. So now, according to the question, we need to change the range, and it should be double. That is, in case 2, we need to change the range I to 2I, and here the question says the additional shunt resistance to be connected across it. So when we are connecting additional shunt resistance, then this is the galvanometer G, the existing resistance is S, so this is S. Suppose we connected an additional resistance, that is S prime. So now the current that will flow through the galvanometer, it is always Ig, which is I by 2, but here the total current that will be flowing is 2I. So in the remaining current, so the remaining current will flow in these two branches. So now if we convert the combination of these two resistance S and S prime, so the resultant resistance S will be, according to the relation, sorry, this, suppose this is S and S prime, so suppose this is S1. So S1 will be 1 by S1 equals to 1 by S plus 1 by S prime. So S1 will be S prime divided by S plus S prime. So this is according to the concept of parallel connection of the resistors. We know when the two resistors are connected in parallel, so the resultant will be the 1 by S1 will be 1 by S plus 1 by S prime. So this is the new combination of the resistance. So now the according to the Kirchhoff's law, like this current into resistance will be equal to the current into resistance in the second branch. So now here it is Ig. So Ig into G is equals to, now the current that will be flowing through in this branch is, so here the current will flow 2I minus Ig. So when we converted it, it will be a single resistance which will be S prime divided by S plus S prime, and the current that will be flowing is 2I minus Ig. So this is the new case. So Ig into G it will be equals to, let me change it. It will be, so it will be Ig into G equals to 2I minus Ig into S prime divided by S plus S prime. And here we need to find out the value of S prime. So let me add another slide. So now we understand the whole scenario. We need to, from this equation, we need to find out the value of S prime. So when we solve it, so the equation is Ig into G equals to 2I minus Ig S prime divided by S plus S prime. We have G equals to 3 ohm, S is again 3 ohm, S prime we need to find out, and Ig we have already calculated, it is I by 2. So it is I by 2 into 3 equals to 2I minus I by 2, 3S prime divided by 3 plus S prime. So it is 3I by 2 equals to 2I minus I by 2, it will be 3I by 2, 3S prime by 3 plus S prime. So 3I by 2, 3I by 2 gets cancelled. So 3S prime equal to 3 plus S prime. So 2S prime is 3, S prime is 3 by 2, S prime is 1.5 ohm. So when we connect, and so this is 3 ohm S, this is S prime. So S is 3 ohm, S prime is 1.5 ohm. Then range will be doubled. So the correct option will be option D, 1.5 ohm. I hope this is clear to everyone. So in the question it was mentioned, there is a galvanometer which has resistance 3 ohm, and we are converting the galvanometer into an ammeter by connecting another shunt resistance of that same value 3 ohm. But now we need to double the range of the ammeter, then the additional shunt resistance we need to connect it, we need to calculate. So first we, in the given condition, we first calculated the current that will be passing through the galvanometer, then we introduce another resistance. So when you introduce a resistor, then the total resultant resistance will be changed. So then correspond to that we had another equation. So when we solve this equation and put the values, we got the additional resistance that need to be connected is 1.5 ohm. So I hope this is clear to everyone. It was a very important question from the point of view of your exams also. So now let's move to question number 3. So question number 3 says, where of length L, area of cross section A, resistance R, and resistivity rho is stressed to 4 times its initial length. The new resistivity of the wire will be, options are option A 4 rho, option B rho by 4, option C rho by 16, and option D rho. So we just discussed one problem. Before one problem we are discussing the concept of resistivity. So this question is again related to the concept of resistivity only. So initially the length of the wire was L and cross sectional area was A. Its resistance was R and resistivity was rho. Now the wire is traced to 4 times its initial length. So now the new L prime is 4L. Then what will be the new resistivity? So this is the question. So I will give you a few minutes to think about this question and try to figure out what will be the correct answer, and then we will discuss. So if you remember the question number 1 that we discussed today, so this question was related to the factors that affect the resistivity of the conductor. So now there we discussed that the resistivity of the conductor is independent of its shape and size. That is the length, the area of cross section under. Unless we are changing the material or the temperature is being changed, the resistivity will remain the same. So the question here also says what is the new resistivity of the wire. So the resistivity of the wire will again be the same, that is rho only, because resistivity is independent. So rho is independent of the shape of the wire. So rho prime will be rho only. So the new resistivity of the wire will be rho. So question number 4, it says in previous question the new resistance will be considered that the volume remains unchanged on stretching. So the same question that of the previous, uh, the length, the wire is traced to 4 times its initial length. So so it was 4 times the initial length. The volume is unchanged. This condition is given, and what will be the new resistance that you need to calculate. The options are option A R, option B 4R, option C 16R, option D R by 16. So these are the 4 options, and I'll give you a few minutes to solve this problem, and then we will discuss what will be the correct one. So if we solve this question, so the expression for resistance is given by R is equals to rho L by A. So now we need to see what are the changes that is occurring when we are stretching the wire to 4 times its length. So on stretching the wire, L prime becomes 4L. So volume is constant. So suppose before stretching LA, after stretching L prime A prime. So L into A equals to L prime into A prime, because volume is constant. So A prime is L A divided by L prime. So L A divided by 4L. So A will be A by 4. So on stretching the wire to 4 times of its length, the area of cross section will also be reduced to 4 times, because the total volume of the wire remains the same, that is there is no compression on stretching. So the length and the area both are changing. So L prime is 4L and A prime is A by 4. Now the new resistance, the new resistance R prime will be rho L prime by A prime. Again, rho is also constant because no materials are being changed and the temperature is also constant, because here in the question there is no information about temperature, so we are assuming temperature is constant. That is, under stretching there is no change in temperature. So what will be R prime? It will be rho into L prime is 4L, A prime is A by 4. It will be 16 into rho L by A. That implies R prime will be 16 into R, because rho L by A was R. So R prime will be equals to 16R. So this is the correct answer. And if you see the options, option C will be the correct one. So when we are stretching the length of the wire, because so when I am stretching the length of the wire, the new resistance that we are getting is 4 times than that of the 16 times than that of the old resistance. Because if you see, when we are passing current through a conductor, so it current flows across the length of the wire. So when we are increasing the length, so we are again introducing more path for electrons to travel from one end to another end. So during that motion from one end to another end, since the path length is more, they will suffer more collisions with the uh, charge carriers like electrons and other then due to that the resistance will be increased. Again, since the area is also getting compressed, there will be further collisions because they have very less space to travel. So these two factors, they will again contribute towards increasing the resistance. So the total resistance that will be getting is 16 times that of the old resistance. This is 16R. Now let's move to question number 5. Question number 5 says, which of the following statement is correct for a voltmeter? Options are: option A, it is a very low resistance and connected in parallel with the resistance of the circuit. Option B, it has a very high resistance and connected in parallel with the resistance of the circuit. Option C, it has a very high resistance and connected in series with the resistance of the circuit. And option D, it has a very low resistance and connected in series with the resistance of the circuit. So we know how we are converting galvanometer into voltmeter. Now the question says, which of the statement is correct for the voltmeter? So I'll give you a few minutes to think about this, then we will discuss. So if you remember, we discussed, so in order to convert galvanometer to voltmeter, we connect a high resistance to series. So when we convert a high resistance to series, so this is the galvanometer and then this is another resistance. So the total resistance of the voltmeter is high. So this is high resistance because this R is quite high. So one thing is clear, voltmeter has high resistance. Voltmeter has voltmeter resistance is high. Now the question is whether voltmeter is connected in series or in parallel. So now what is the main aim of the voltmeter? The main aim of the voltmeter is to measure the voltage that is passing through a terminal, or the voltage drop across a particular element. And we know, according to Kirchhoff's law, sorry, the current remains constant in a series and the voltage remains constant in a parallel connection. So when we are connecting the voltmeter, it should be connected in parallel only, because in that case it will measure the same voltage that is dropping across the terminal that we actually want to measure. Also, the voltmeter must be connected in parallel because it measures a potential difference between the 2 points in the circuit. So the voltmeter, for an ideal voltmeter, the resistance should be high. Very high means, for an ideal voltmeter, the resistance will be, so the resistance should be infinite. And another thing is, so what is the value of voltage? So voltage is I into R. So V is equals to IR. Suppose this is a circuit, this has something, so we want to measure the voltage that is getting dropped across this element. Suppose this is an electrical element, and then the current is flowing. This is the current I, and we need to measure the voltage drop across this element. So what we want? We want the majority of the current to flow through this electrical element only, and the circuit should not be getting disturbed in introduction of the voltmeter. That's why voltmeters are generally have, since the voltmeters are generally have high resistance, so they will draw a very less current when they are connected in parallel. So when the resistance is high, the current will be reduced. So here very less current will be passing, and majority of the current it will flow. So I2 is nearly equals to I. So the majority of the current that will flow through the electrical element, and since the majority of the current flows, so the voltage drop will be the actual voltage that we want to measure. So the correct option is, the voltmeter is a very high resistance and it is parallel connected in parallel with the resistance of the circuit. So there will be no error when we are connecting it in parallel. I hope this explains this answer. Now we'll move to question number 6. Question number 6 says around 27.0724 to the nearest tenth. Options are option A 27.0, option B 27.07, option C 27.1, and option D 27.2. So the 10th place digit, what is the 10th place digit? So 27.0724. So this is 10th place, this is 100th place, this is 1000th place, and this is 10,000th place. So the 10th place is 0, so we need to round it to the nearest tenth. So the next digit to 0 is 7. So 7 is greater than 5, so the 0 will be changed to 1. So 27.0724, when we convert it to nearest tenth, it will be 27.1. So the 0.07, it will be converted into 0.1 as 7 is greater than 5. So this is the answer, and the correct option is option C. I hope this is clear to everyone. These type of problems we have solved many times in the last interaction session also. So now let's move to another question that is again based on the significant figures. The number is 875,000, and we know all trailing zeros after non-zero digits, they are not significant. So here this is not significant, this is not significant, and this is not. So these three are significant digits. So the number of significant digit in this figure 875000 is 3. So the correct option is option 3. I hope this is clear again. Now we move to the question number 8. Question number 8 says the volume of 50.8 gram of iron is 6.5 centimeter cube. Express the density of iron by keeping the significant figures in view. Options are option A 7.815 gram per centimeter cube, option B 7.8 grams per centimeter cube, option C 7.82 grams per centimeter cube, and option D 8.0 grams per centimeter cube. So these are the four options, and we need to find the density by keeping the significant figures in view. So we need to keep in mind the number of significant figures should be according to the rule of the division and multiplication related to the significant figures. So these are the four options. I'll give a few minutes to think about this question, and then we will discuss what will be the correct one. so which is called as Lorentz force. So when the particle moves inside a magnetic field, the force experienced by it is called as Lorentz force, and the expression for force is F is Q B cross B vector. So Q is the charge, B is the velocity, and B is the magnetic field. Now in question, so it will be F is equals to B Q V sin theta, where theta is angle between V and B. Now in the question it says V and B are in the same direction. So V and B are in the same direction. That implies theta is 0 degree. So F will be QBV sin theta QBB sin 0 degree QBB into 0, which is 0. That is no force. So the correct answer will be option D. So when a charged particle moves inside a magnetic field, it experiences a force which is given by V cross B, and this is called as Lorentz force, or it is QBB sin theta. So when theta is 0 degree or 180 degree, that we just saw, force is 0. So there will be no force. So the particle will move along its old trajectory. So it will be linear. So the particle where it was moving, it will experience no force. So when theta is equals to 90 degree, the force will be maximum, and the path under that force will be circular, because since here you see the direction of the force is perpendicular to both the magnetic field and both the direction of motion, that is velocity. So when the particle is moving along x direction, it will experience uh, when the particle is moving along x direction, and it will be experiencing forces along y or z direction, and that will result in the circular motion of the particle. So when the particle undergoes a circular motion, we know mv square by r is the centrifugal force, which is supplied by this magnetic field force, which is b q v. So if you solve it, so r will be mv by qb. So this is called as Larmor radius. So the radius of the particle when it undergoes circular motion or the cyclotron motion in a magnetic field, the radius is called as Larmor radius. So one of the option was that also this mb by qb. So mb by qb is not force but the radius of the circular path of that particle. And there is another case when theta is, so when theta is 0 to 90 degree. So it is neither 0 neither 90 degree, it is between 0 to 90 degree. Then there will be helix, because uh, the component that will be along the direction, it will help in moving along the direction of the motion, and the force acting on the perpendicular direction, it will help in circular motion. So the particle will undergo circular motion, but the center will move along a linear direction. So if we want to see, so suppose so this is circle when theta is 90 degree, but when theta is not 90 degree, it will be like this. So this point, this will move in a linear direction. This is called as guiding center. The guiding center will move along the x direction and the particle will gyrate in perpendicular plane, that is YZ plane. I hope this clears your concept regarding the motion of a charged particle in magnetic field. Now let's move to question number 10. Question number 10 says, at a distance of 10 centimeter from a long straight wire carrying current, the magnetic field is 0.04 Tesla. At the distance of 20 centimeter, the magnetic field will be. So when uh, a conductor carries current, then it produces a magnetic field around it, and we need to find out. So for a particular case, it is given that at the distance of 10 centimeter, the magnetic field is, so when D is 10 centimeter, magnetic field is 0.04 Tesla. Now when the distance is 20 centimeter, what is the magnetic field? Sorry, that we need to calculate. So the options are option A 0.01 Tesla, option B 0.02 Tesla, option C 0.08 Tesla, or option D 0.16 Tesla. So I'll give you a few minutes to solve it and then we will discuss. So if you discuss about the magnetic field that is getting produced by a current carrying wire, it is governed by Biot-Savart's law. So according to Biot-Savart's law, if you take a small element, the magnetic field produced by the small element at a distance r is given by mu 0 by 4 pi I dl vector cross r cap divided by r square. So this I is the current flowing, and mu 0, this is permittivity of the free space, permittivity of the free space, and the value of mu 0 is 4 pi into 10 to the power minus 7 Henry per meter, and this r is the distance from the wire. So if you calculate it for a long current, long infinite wire, then the expression reduced to mu 0 by 4 pi 2I by d. So for the case given, d is 10 centimeter, b is 0.04 Tesla. So now d is 20 centimeter. So b is inversely proportional to d. So since d is getting 2 times, so b will be b by 2. So 0.04 by 2, that is 0.02 Tesla. Or you can direct put value of d here 10, it is 0.04. So if you put 20, so since d is 2 times, b will be reduced 2 times, that is 0.02 Tesla. Now let's discuss about the direction of that magnetic field. So the direction of that magnetic field is given by right hand thumb rule. Right hand thumb rule. So when the so when the now make a so fist of your in by your right hand. Now the direction of the thumb is the direction of the current flowing through that current carrying conductor, and the direction of your fingers will give you the direction of the magnetic field or the magnetic lines of force. So here this is the direction of the current carrying conductor, which is dot means the direction is away from the plane. So if the direction, suppose this is the direction, then it will be the direction of the magnetic field will be like this. So this is the direction, that this is the direction of the magnetic field. This is the direction of the current, and this is the direction of the magnetic field. This is one demonstration. So I hope this is clear to everyone. So with this we come to the end of today's interaction session. We have two problems more, that is again based on the recent concept that we have studied. So uh, I thank you all for this for joining in this course and this interaction session. So I hope you will be attending the interaction session regularly in the near future. With this, I come to the end, and that's it for my side today.